Dear students, I am Mahesh Javalkar from Maratha Mandal Polytechnic, and today I am going to introduce a next member of the thyristor family, which is called as TRIAC. Okay, so if you see the definition of the TRIAC, you can see it like this. A triac is a three-terminal electronic component that conducts current in either direction when it is triggered. Okay, so it is having three terminals. They are named as MT1, MT2, and gate. Okay, and here the MT1 and MT2 are main terminal 1 and main terminal 2, which can anyone can be positive and anyone can be negative. Similarly, gate also pulse whatever we are going to give can be positive or negative, and it can conduct in both directional. It is a bidirectional device. Okay, so here it is same like SCR in the characteristics, but it is in both quadrant. It can conduct in both direction. It can show the characteristics in the graph in the first quadrant also and in the third quadrant also. Okay. Then we will go to see the layer diagram of track. So a track actually has five layers, out of which four layers will be working effectively whenever the terminals are positive and negative. Okay, so here you can see layer P1 here, layer P1 here, then you have N1 here, then you have P2 here, okay, and then you have N2 here. Okay, now this P1, N1, P2, N2, this is a flow of current when MT2, that is main terminal 2, is made positive. That is when MT2 is positive, okay, is positive, and MT1 is negative. MT1 is negative. Then the flow of current will be from layers P1, N1, P2, N2. Okay. So here you can see this P1 and N3 are together connected in this metal contact here. So whenever MT2 is positive and MT1 is negative, then P1 will be effective, then P1, N1, P2, N2 will be the current flow for positive and negative gate pulse. Okay. Similarly, when MT1 is made positive, okay. Similarly, when MT1 is made positive with respect to MT2, okay. So here we'll just write it. MT1 is positive with respect to MT2. So MT2 is negative. Okay. Then we have to start from here. So this is positive here. So here if this is positive, you can see this metal contact which is for N2 and P2, and this contact is for N4 and P2 for the gate. So here once MT1 is positive, then the effective side semiconductor layer will be P2. Then you have to go from P2, N1, P1, N3. Okay, so there it will go as P2, N1, P1, N3. Okay, so here the flow of current will be P2, N1, P1, and N3. Okay, so it will be from MT1 to MT2 because MT1 will be at higher potential with respect to MT2. Clear? That means it can conduct in both directions, and it will be triggered either by overcoming the breakover voltage or by gate pulse. Means what will happen? Say for example, when MT2 is positive with respect to MT1, then the junction between P1 and N1, that is this junction, P1 N1 junction will be forward bias. Okay, N1 P2 will be reverse bias. This will be reverse bias. Okay, and P2 N2 will be forward bias. Okay, so this reverse bias have to go into breakdown if you want to conduct the triac. So if you work only on breakover voltage, then the voltage between MT1 and MT2 should be such that the second junction goes into breakdown and triac goes on. Okay, otherwise if the voltage is kept at some minimal value, okay, and if you apply a gate pulse, whether the gate pulse is positive or negative, here you can see the gate terminal, the gate pulse is positive or negative. This is a gate pulse, it can be positive or it can be negative. So, okay, so that gate pulse will see that the second junction goes into breakdown. Okay, so there, second junction has to go into breakdown for the triac to become on. Clear? Then, if you make the empty one terminal as positive with respect to empty two, then the first junction between P2 and N1, that is this one, will be forward biased. That is, this will be forward biased. N1 P1 will be reverse bias, and P1 N3 will be forward biased. Okay. So here in this way, the second junction again will be reverse bias, and the second junction can be made to go into breakdown if the applied voltage between MT1 and MT2 crosses the breakover voltage, or you apply a gate pulse of positive or negative, then it can go into breakdown. Okay. So this is how your a track is going to work. So looking at this working, okay, we can conclude that track works in four modes. Four modes means how? Once MT2 is positive, MT1 is negative, gate pulse can be positive or negative. These are two modes. And then another time MT1 is positive, MT2 is negative, and then you can make gate pulse plus or minus. That is another two modes. So totally four modes in which it can work, and we will see those modes now. Okay. So here you can see, the definition and the structural description of a triac. A triac is a five-layer, three-terminal semiconductor device. The terminals are marked as MT1, MT2, that is main terminal 1, main terminal 2, as anode and cathode terminals in case of SCR. And the gate is represented as G, which is similar to the thyristor. The gate terminal is connected to both N4 and P2 regions by a metallic contact, and it is near the MT1 terminal. Okay. The terminal MT1 is connected to both N2 and P2 regions, while MT2 is connected to both N3 and P1 regions. Hence, the terminals MT1 and MT2 connected to both P and N regions of the device, and thus the polarity of applied voltage between these two terminals decides the current flow through the layers of the device, which is what we have discussed earlier to this. Then we will see how the symbol looks. So here you can see the symbol of a track. You can see like two SCRs. You can see this is SCR1 and this is SCR2. So this is your SCR1, and this is your SCR2. So they are in anti-parallel. So two SCRs in anti-parallel, and one terminal on top you can see, which will be called as main terminal MT2. Okay, main terminal 2, and one terminal here which is called as MT1, and here you see a common gate which can be applied as a positive pulse or negative pulse, whereas in SCR it was only positive pulse, whereas here in TRIAC it can be, a gate can be positive or negative. Okay, so here you can see the a diagram again, inverse parallel of SCR pair as we have shown here. So here you can see one SCR1 is here, and this is one SCR, and then you have another SCR. So this is one SCR, this is the second SCR. So both are in anti-parallel, and the common triac symbol is shown in figure A. Okay. Then we'll go to see that when the gate open, when the gate is open, MT2 is made positive with respect to MT1 for a forward bias triac. Hence, triac operates in forward blocking mode until the voltage across the triac is less than the forward breakover voltage. Similarly, for a reverse bias triac, MT2 is made negative with respect to MT1 with gate open. Until the voltage across the track is less than a reverse breakover voltage, device operates in reverse blocking mode. A track can be made conductive by either positive or negative voltage at the gate terminal. This is what we have spoken when we explain the layer diagram of track. Okay. Then we'll go to see what are the modes of track. Okay. So it is possible to connect various combinations of negative and positive voltages to the track because it is a bidirectional device. So the four possible ways are as follows. Number one, if you see, MT2 is made positive with respect to MT1 with a gate polarity positive. That means MT2 is positive and MT1 is negative. So in this first mode, you can see in this first mode, MT2 is positive, MT2 is positive, and MT1 is negative, MT1 is negative, and gate is positive. Gate is positive. Okay, this is the first mode. Okay, this is the first mode in which you're working. In the second mode, if you see, MT2 is made positive with respect to MT1, same as the first mode. Only thing the gate will be negative. Only thing the gate will be negative here. Okay. In the third mode, you see, MT2 is made negative with respect to MT1 with gate polarity negative. Okay. And in the fourth, you see, MT2 is made negative with respect to MT1 with gate polarity positive. Okay. So in the first two cases, in the first two modes, MT2 is positive, MT1 is negative, and gate is positive in the first mode and gate is negative in the second mode. In the third and fourth mode, MT2 is negative and MT1 is positive, with gate becoming negative in the third mode and gate becoming positive in the fourth mode. Okay, so in this way, four different operating modes are there for a triac. Clear? Then you can see here the mode 1, a terminal MT2 and gate are positive with respect to terminal MT1. Then the main important thing what you have to remember here is when MT2 is made positive with respect to MT1. Okay, so this is positive. MT2 is made positive with respect to MT1. So MT1 is negative. Okay, and your gate terminal is positive. This is positive. So, okay, so in this way, if MT2 is becoming positive, then the layers which come into picture are P1 will be the first layer, N1 will be the second layer, P2 will be the third layer, and N2 will be the fourth layer. Okay, so in this way it is going to work. So here you can see in the description the current flow path. So here you can see the current flow path, that is P1, N1, P2, N2. Okay, so that is what you have to remember here when MT2 is becoming positive with respect to MT1. Now in this case, we have said the gate is positive. A positive gate with respect to terminal MT1 will forward biases the P2 N2 junction and the breakdown occurs as in normal SCR. Okay, that means one thing you have to remember here is the flow of current will be P1, N1, P2, N2 when MT2 is positive with respect to MT1. Now in this case, in first mode, we have kept gate as positive. In the second mode now, the same thing will be there. MT2 is positive with respect to MT1. Okay, so here you can see MT2 is positive with respect to MT1. So MT1 is negative. And here gate we are making it as a negative supply. Okay, so here the gate will be negative supply. Okay, so in this case, when MT2 is positive with respect to MT1, again the flow of current will be same P1, N1, P2, N2. Okay, so here you can see the P1 will be the first layer, second layer, third layer, and fourth layer. It will be same. Only thing the gate or triggering pulse of the gate will be negative. Okay, so here P2 and 3 will be in forward biased, and then the current carriers injected to P2 will turn on the triac. Okay, so in this way, the flow of current will be same as mode 1. Only thing the gate pulse will be negative over here. In the third mode, what will happen is MT2 is made negative. MT2 is made negative. So here you can see this is negative with respect to MT1. So MT1 is positive here. So MT1 is positive here. And the gate terminal is negative. This is negative. So here you can see a negative gate terminal. Once MT1 is positive, then you have to start with P2. This will be the first layer, then N1 will be the second layer. So here you can see the second layer. Then P1 will be the third layer. P1 will be the third layer. So here you can see it will be the third layer, and N3 will be the fourth layer. So the flow of current will be P2, N1, P1, N3. Okay. Now in this case, the gate is negative. Okay. So a negative gate with respect to terminal MT1 injects current carriers by forward biasing the junction P2 and 4 and thus initiates the conduction. But the main thing is, how does the current flow? So here we have mentioned the current flow as P2, N1, P1, N3. Okay. So this is the way the current will flow in mode 3. And the same way the current will flow in mode 4 also. Only thing in mode 4, the gate terminal will be made positive. Okay. So if you see the mode 4, again here MT2 will be negative. So here MT2 will be negative and MT1 will be positive. Okay. So here you can see in the diagram what we have shown. MT2 will be negative and here down MT1 will be positive. With respect to gate will be positive in this case. Okay. Now once MT1 is positive, again the same thing. P1 will be the first layer, N1 will be the second layer, P1 will be the third layer, and N3 will be the fourth layer. So P2 will be the first layer, N1 will be the second layer, P1 will be the third layer, and N3 will be the fourth layer. So this is how the current is going to flow. This is how the current is going to flow. Okay. So here only a difference between third and fourth mode is now the gate pulse will be positive. Okay. Once the gate pulse is positive, P2 N2 is in forward bias, current carriers are injected and therefore the triac becomes on. So in this way, there are four different ways or four different modes in which triac is going to work. If you see the VI characteristics of triac, you can see here the x-axis is taken as voltage and the y-axis is taken for current. Okay, so if you don't give any gate pulse, okay, and if you make MT2 positive with respect to MT1, so here you can take this as MT2 positive, MT1 negative, okay, and you are going to give a gate pulse. Okay, so here in this case, if there is no gate pulse, initially the current will be very small. So here you can see a very small current which is there. So this is a part where a very small leakage current is there because your second junction is a reverse bias. Then once you reach this point, once you reach this breakover voltage without the gate supply, you have to come till this voltage, then the triac will become on and then the voltage across the triac will decrease and the current will start increasing here. So the voltage will decrease and the current will start increasing here. Okay. Similarly, if you give a gate pulse of a little lesser magnitude, then this will go into conduction early. If you give a little more gate pulse of higher potential, then it will conduct here. If you give more gate pulse, then it will conduct here. Okay, that means as the potential of the gate pulse is more, it will go into conduction early. Okay, now similar thing will happen in quadrant 3 also, where you're going to just change MT2 will be negative and MT1 will be positive for the gate pulse. Okay, for the gate pulse. So here you can see if there is no gate, you have to come till here. So here where the minus VBO is the voltage where the breakover takes place when the gate is 0. But if you just uh, change the magnitude of the gate. So depending upon the magnitude of the gate, this will go into conduction early, this will go more early, and this will go more early. It will conduct, voltage will decrease, and current will go on increasing in the negative side. Okay. So in this way, it will show characteristics same like SCR in the first quadrant and the third quadrant. Okay, so it is a bidirectional device. So here is the VI characteristics of your triac. So if you explain the VI characteristics, you can say that the triac function like a two thyristors connected in antiparallel, and hence the VI characteristics of the triac in the first and third quadrants will be similar to the VI characteristics of the thyristor. When the terminal MT2 is positive with respect to MT1, the triac is said to be in forward blocking mode. A small leakage current flows through the device provided that the voltage across the device is lower than the breakover voltage. Once the breakover voltage of the device is reached, then the triac turns on as shown in the figure. However, it is also possible to turn on the triac below the breakover voltage VBO by applying a gate pulse in such that the current through the device should be more than the latching current of the triac. Okay. So similarly, when the terminal MT2 is made negative with respect to MT1, the triac is in reverse blocking mode. A small leakage current flows through the device until it is triggered by breakover voltage or gate triggering method. Hence, the positive or negative pulse of the gate triggers the triac in both directions. This is what we have seen in the theory in the working of triac. Okay. Then advantages of a triac are triac can be triggered by both positive and negative polarity voltages applied at the gate. Because this in a comparison with SCR, SCR can be triggered only by positive gate pulse, whereas triac can be triggered by both positive and negative gate pulse. Okay. It can operate and switch both half cycles of an AC waveform. That means it is a bidirectional working, whereas SCR was only in one direction, unidirectional working. Okay, as compared with anti-parallel thyristor configuration, which requires two heat sinks. Okay, a triac needs only a single heat sink of slightly larger size. Hence, the triac saves both space and cost in AC power applications. Okay. In DC applications, SCRs are required to be connected with a parallel diode to protect against reverse voltage, but the triac may work without a diode. A safe breakdown is possible in either direction. This is also one more advantage of your triac. Then we'll go to see the disadvantages. These are available in lower ratings as compared with thyristors. So as compared with SCRs, the triacs can handle lesser current, lesser voltage, and lesser power, whereas SCR can handle more current, more voltage, and more power. Okay. A careful consideration is required while selecting a gate trigger circuit, since the triac can be triggered in both forward and reverse bias condition. They have low dV by dt rating as compared with thyristors. These have very small switching frequencies, and our triacs are less reliable than the SCRs. Okay, then we'll go to the next point. Different types of triac packages are available in the market, and they are like first one is pin standard type, second one is capsule disc type, and the third one is stud type. Okay, so if you see the pin standard type, you can see this figure in which you can see there are three terminals. So these three terminals are your MT1, MT2, and gate. So here you can see a terminal 1, terminal 2, and terminal 3. So this is your 1, this is 2, and this is 3. Okay, so here you can see the three pins which are there are your MT1, MT2, and gate. That is main terminal 1, main terminal 2, and gate. And a heat sink on the top. This type of triacs are used in domestic electronic appliances. Okay. Now here students will see the second type, which is called as capsule or disc type. This type of triac will be the shape of the disc with extended wires to the terminals. These triacs have a high current capability and are made with a ceramic seal. They can be used in applications such as fast motor control and AC switching. Stud type. The stud type triac are mostly used in high power applications. They have a screwed bottom that acts as one of the main terminals and has two terminals on its top, which are the other main terminals and gates. Similarly, here also you can see one MT2 at the bottom, and on the top you have two things, which is your MT1 and gate. So here in this figure you can see the stud type of triac. Okay. Then, if you go to see the applications, due to the bidirectional control of AC, tracks are used in the following. Number one is AC power controllers. Second one is fan controllers. Third one is heater controllers. Fourth one is triggering devices for SCRs. Fifth one is three position static switch. And sixth one is light dimmers. Okay, and many more circuits are there where you can use tracks, but these are some of the important ones. Okay, thank you students for watching this video on track. In my next video, I will take the next device of the power electronics. Thank you very much.